Well, welcome again to our little journey through some number theory, and we've looked at the sum of two squares in the previous section, and I'm going to move on now to Pythagorean triples. And so before we look at 3 and 4 squares, I want to digress briefly to have a look at these Pythagorean triples. And of course you'll remember that a triple of numbers, triple of positive integers, is called a Pythagorean triad or Pythagorean triple if the sum of the first squares of the first two is the square of that one, i.e. these form the sides of a right-angled triangle. And we want to find all such triples. I want to find some nice simple formulae that will give me all possible Pythagorean triples. Now the first thing I'm going to do is probably what you don't do in number theory generally, and that is to go from integers to fractions, because fractions are often more complicated, but I'm going to break that rule here. I'm going to take this equation and I'm going to divide everything by z squared, and I'm going to write it like this. And of course if you call that one capital X and that one capital Y, you're now staring at a unit circle. And you can see then that if x, y, z are positive integers, then these things are going to be rational numbers. And if I put x equals that and y equals that, I get the circle x squared plus y squared is 1. So we can see then that given integers x, y, and z that are Pythagorean triples, then the equation that has rational solutions, because there they are here. And conversely, if we can find rational solutions to this, then we can express the x and y with the same denominator and then get integers x, y, z that make this true. So the problem of finding triads is equivalent to the problem of finding rational points on this circle. Note the correspondence is not one-to-one, so for example you can get that one and that one from the same rational point, this one. However, if we insist that the GCD is 1 and the correspondence is 1-to-1, well, you might think, well, you've turned what was already a difficult problem, finding all integer solutions of that, into something that looks even more complicated, that is to find all rational solutions, positive rational solutions on this unit circle. Well, it turns out, using a little trick that in fact I think goes back to Fermat, that this is actually a sensible thing to do, and in fact there's a lot of interesting mathematics of this leads on from this kind of approach. Okay, so we introduce some geometry, so I'm going to draw this circle. So this is the circle x squared plus y squared is 1. And this is the line y equals tx plus 1. So we consider this circle that passes through the point -1, 0. There's my circle. This will be 1 there, of course. And I'm going to draw a line that passes through this point. I'm going to draw a line with gradient t. So the slope of this line will be t. And it's going to meet the circle somewhere here at some point x, y. Now I'm going to restrict t to be a rational number between 0 and 1. So if it's 0, the line will be there, and if it's 1, the line will be there. So this line is going to intersect the circle at points in the first quadrant. Now it's easy to get the equation of the line. It's trivial. It's t into x plus 1, which you can see immediately from here. And I want to find where this line cuts the axis. So firstly observe that if x, y, if this, forgetting that for the moment, if this intersection here is a rational point, then t, which I can write by just rearranging this line here, t is also rational. And conversely, if t is rational, solving the line that with the circle is going to give us rational points. Indeed, we do that. So I'll leave you to check the algebra here. I'm just going to replace the y with tx plus 1. So I get x squared plus t squared x plus 1 all squared, which I just equals 1. I just rearrange that equation and it turns into this quadratic. I'll leave you to check the algebra there. Now, so let's just enjoy this quadratic. We've got a quadratic here. We know one of the roots of it. One of the roots is minus 1 because this line passes through here. So one of the roots is x equals minus 1. So we can use we don't need to solve this quadratic because we just use the product of the roots. So the product of the roots is going to be this number over this number. And the product of the roots then is going to be minus, because of the minus 1, we're going to get minus capital X as that. And so I can rearrange and just get X is equal to minus this one over this one. So it's 1 minus t squared and 1 plus t squared. And then I can get the Y by substituting, well, I can do lots of things. I can substitute this back into here and then simplify and solve for Y, and we find we get 2t on 1 plus t squared. Now, the assiduous reader will recognise that this is looking very suspiciously like the double angle formulae from trigonometry, the tan theta on 2 formula. And indeed, I leave you to see how they're connected to each other. I'll give you a little hint. If you join this line down to here, this angle here is theta around here, and you might like to think about what this angle in here is, and see the connection between these formulae and the tan half angle formulae. However, in our case, we've seen then that if you've got a rational point, it corresponds to a rational gradient of the line, and if you've got a rational gradient, it corresponds to rational points. So if t is rational number strictly between 0 and 1, then x and y will also be rational. So, just as a quick example here, if I take t to be, say I just picked a fraction at random, 73 on 91, seemed a nice fraction, and I plug that in to my formula here, I get xy are these fractions here, 2952 on 13610 for x, and 13,286 over the same denominator. That means then that that number, and the denominator form a Pythagorean triad. That is, that squared plus that squared is that squared. Well, we can now construct our general formula. I simply do what I did here, except instead of putting specific numbers, I'm going to put u over v for t, and I plug that into my formula for x and simplify. We get v squared minus u squared on u squared plus v squared, and I plug this in to the formula for y up here, and I get a formula for the y. It's 2uv on v squared plus u squared. Now, that means I get a triple, which is that number, and the bottom, but remember I could have put some k on top and bottom here, because we want to get all solutions. So I'm going to multiply top and bottom by k firstly. Then I can take little x is k times that number, plus little y is k times that number, and little z is k times the denominator, where k is an integer. And now to make this positive, of course, I need v to be bigger than u, and I need everything positive. So this formula, or these formulae here, now give me the formula for all Pythagorean triples, Pythagorean triads. So for example, I put k as 1 in, I just picked a couple of primes, don't have to be primes, just a couple of positive numbers, making sure that that's less than that one. Plug these into the formula here and I end up with that triad. By the way, notice this is not what we call a primitive triad, because you could divide this by 2 and you'll get a smaller one. So we have to, we'll come back and look at that question. How do we get just the so-called primitive triads, the ones with no common factors? The k, by the way, is important if you want to get all the triads. For example, if k is only ever equal to 1, if you put k as 1 into these equations, then you try and construct this triad. Well, you can't. So you simply putting k equals 1 is not sufficient to get all the triads. You really need a general k there. You can't get this triad, for example, if k is 1. Okay, well, primitive triads, well, if A, B and C is a triad and the GCD of the three numbers is 1, then we call this triad a primitive triad. And if you think about it a little bit, firstly, in this case, to get primitive triads, you need, of course, k to be 1. And you've got to be careful also, because if u and v have a common factor, then obviously these will have a common factor. So you want u and v to be relatively prime. And you might think, well, that'll be sufficient. I put k as 1, u and v relatively prime, but that doesn't quite work, because if u and v are both odd, then this will be even, and this is even, and this is even, and so you get a common factor of 2. So the full story, the proper story, is to get primitive triads, you need k as 1, you need the GCD of these to be 1, they've got to be relatively prime, and they must have opposite parity. That is, they can't both be odd, so you'll need one even and one odd. They have to have opposite parity. So for example, if I put 5 and 7, these don't have opposite parity. These do not yield a primitive triad, as we saw in the above example. These numbers were relatively prime, k was 1, but this was not primitive. Okay, well, I'm going to just, again, before we move on to sums of other numbers of squares, I wanted to do a little application of this to Fermat's last theorem for n equals 4. And this, in fact, goes back, I think, to Fermat managed to do this himself. Fermat, of course, claimed that this general equation, x to the n plus y to the n, z to the n, where n, x, y and z are all positive integers, this has no positive integer solutions if n is bigger or equal to 3. And of course, you know the famous saying that he wrote in the margin of his book that he had a most excellent proof of this fact, but the margin was too small to contain it. Well, I think he was probably seriously misled, because this result has been proven, but only fairly recently, using quite sophisticated mathematics. So he, as I said, he claimed to have a proof, but he never wrote it down, and it's only recently been proved using very advanced techniques. And the problem is generally referred to as Fermat's last theorem, and what was, until it was solved, one of the holy grails of mathematics, because it was such a simple problem to state and yet so difficult to prove. However, Fermat, I think, did have a proof for the case when n equals 4, and I think it was somewhat similar to what I'm going to do here. And we're going to use a method that seems to have first been used by Fermat, called the method of infinite descent. So we firstly note that this equation has, if it's got integer solutions, that is non-trivial, that is, obviously you could put y to be 0 and then x equals z, so non-trivial integer solutions when I write that, then so does this equation. That is, I can replace the z fourth with z to z squared, because this is just z squared all squared. So I'm going to concentrate on this equation here. So suppose we have x, y, z that satisfies this equation here. And I'm going to insist now that z be as small as possible. That is important. So of all the solutions that this has, there must be one with z as small as possible, but of course not 0. The idea then is I'm going to find 3 new integers, capital X, capital Y, capital Z, that satisfy this equation, but the z is small, capital Z is smaller than little z, and little z was supposedly the smallest one, and that will contradict the minimality of z. This method is sometimes known as the method of infinite descent, appears to have been first used by Fermat. It's kind of like induction backwards, you might like to think about that. It's kind of like an induction but backwards. So we may suppose that these have no common factor, otherwise you could have divided it out, and z wouldn't be as small as possible, and also that the GCD of x and y is 1, because again, if the GCD is not 1, then you could divide it out and get as small as z. So that means then so this is x squared all squared, this is y squared all squared, and this is z squared. So x squared, y squared, and z, that forms a primitive Pythagorean triad. So I can write this as x is p squared minus q squared, y squared is 2pq, and z is p squared plus q squared, where p and q are relatively prime with opposite parity. So I used u's and v's before, I'm just using p's and q's, it's just the same thing. Now if p is even, so there's two things to worry about. These have to have opposite parity, so one of these two is even and one of them's got to be odd. If p is even and q is odd, then in that case, when you read this equation modulo 4, an even number squared is 0 mod 4, an odd number squared is going to be 1 mod 4, and then that would give me then x squared is, from here, this gives me x squared then is congruent to 3 modulo 4, and that's impossible. So if p is even, then we're going to get q squared modulo 4 I said is 1. That'll give me x squared is minus 1, which is 3 modulo 4, and that's impossible. So that means p is odd and q is even. So if q is even, I'm going to call it 2r. And now I just plonk that into the defining equation. So x squared now is p squared minus 2r squared. And I can take that 2 from, I can take this here and I can write this as 1/2 of y squared is pr. So I get a 4 there, I can pull it underneath as 2 squared. Maybe to check the algebra here, the GCD of p and r is 1. Now the second equation, this second equation implies that, that's this equation here, this tells me that p and r, they've got no common factor, and the product is a square, so each of these numbers is itself, are themselves perfect squares. So I can put p as capital Z squared, r as capital W squared. Okay, and now I can then plug that back into this first equation, so I get x squared plus 2w squared squared is z to the 4th. Well, now I get another Pythagorean primitive triad, because I've got x squared, 2w squared all squared, so 2w squared, and z to the 4th is z squared squared. So that is a Pythagorean triad. And I can again write down explicitly what the formula for these are. So x is going to be p squared minus q squared, 2w squared is 2pq, and z squared is p squared plus q squared, where GCD of p and q is 1 and they have opposite parity. Now, so I should have perhaps written there here, p and q have opposite parity. Now, by the way, you say, well, hang on, you could have put this one in there and that one in there. Well, if I did that, if 2w squared was the p squared minus q squared, well, that's not possible because p and q have opposite parity, which means the difference of their squares will be odd, and this is clearly even. Okay, so there was a choice there, but you can't make the other choice. So that's forced. Finally, the second equation, that's this one here, to cancel out the 2's, p and q are relatively prime, so p and q themselves are both squares. And so I'm going to put capital X squared as to p and capital Y squared as q. So if p and q are both squares, then they're squares of something. And then from the third equation, if I plug that finally into here, I get x to the 4th plus y to the 4th is z squared, which is the equation I started with different x, y's and z's. Now z squared, chasing everything back, z squared was equal to p, and p was the square root of little z minus q squared by just chasing back the earlier equations. The square root of z minus q squared is less than root z. Root z, because z is an integer, is less than z, and then less than z squared. And comparing these two, we find z is less than x, and that contradicts the minimality of z. So that's a nice little application of the formula for Pythagorean triples to the n equals 4 case of Fermat's last theorem. In the next video, we'll have a look at the sum of 3 and 4 squares.